Hello! This week we're going to be starting our discussion about vectors. Now, we're going to look at vectors in Euclidean n-space, and that's just a fancy word for talking about vectors where we've got a bunch of real numbers separated by commas and surrounded with round brackets. Now, we call those individual numbers, we call them the components of the vector. And we say that the number of components there are, that's the dimension of the space where that vector is in. So for instance, if we have R2, we've used that notation before, I believe, it's the Cartesian plane. So if I have a vector in R2, I might have, say, 4, -3. This is a vector in R2. For R3, it means I've got 3 real components. Let me start to get fancy a bit here. There's all sorts of numbers that are real numbers. So there's a vector in R3, and of course R7 just has 7 components for all its vectors. There you are. Now, for two vectors, to say that they're equal, it means two things, kind of the obvious intuitive things. First of all, they have to be in the same space. That means they have to have the same number of components. So if one of them has 3 components, the other one has to have 3 components. And not only that, you have to have that all of the components are identical and in the exact same order. So two vectors are equal means that they're completely identical when we look at them. That's fairly straightforward. And then we've got some vector arithmetic. Now that we've defined what vectors are in Euclidean n-space, we can start to create a bit of arithmetic around them. We can talk about adding vectors, or we've got vector subtraction. And finally, we have something a little bit new called scalar multiplication. For scalar multiplication, what you have is k, which is some real number. We call it a scalar. And then you have some vector, and we use this little over arrow symbol to denote a vector usually. So we might see, like we do above, there's kind of all the components, but then that gets a bit tedious to write out, so we have this little notation that just has one symbol that will represent that whole complicated vector. All right? So getting back to scalar multiplication, it works when we have some real number, which we call a scalar, and we do scalar multiplication with some vector. And how does it work? Well, all you do is you multiply every component by the scalar. All right, so we can do those simple arithmetic operations with vectors. Now, one tiny little note, if we want to add two vectors together, they have to be in the same space. So they have to have the same number of components. And the same is true for subtraction. If we want to subtract two vectors, we better make sure those vectors have the same number of components. All right, let's try some examples here. So at the top here, we see two different vectors, u and v, and we're going to calculate a bunch of different arithmetic expressions. We're going to simplify them. So if we just straight up add them up, we're going to get -3 plus 5 will be my new first component, 2 plus 0 will be my second component, and 4 minus 1 will be my third component. I'm just adding up the pairwise components here. And then, of course, all those little calculations, very simple. We get the vector 2, 2, 3. Okay. Now, if we do subtraction, I take the components of u and subtract the corresponding components of v. And, of course, we're going to get here -8, 2, and 5. Now for scalar multiplication, if I take v here and multiply it by the scalar -3, so let's write down v here, all I'm going to do is multiply each component by -3. So we get the vector negative 15, 0, and 3. Okay. Now, for those first few examples, they're really easy, and you can just jump straight to the answer. I just want to show it in the long form for now so that you can see exactly what's going on. Now, we can combine these things together, and we create something called a linear combination. We're not going to talk too much about that in this class, but in your linear algebra courses, you're going to talk a bit about linear combinations. It's just a fancy word for saying we're taking scalar multiples of our various vectors and then adding up the results. So if I do negative 8 times u, I would get, well, we can do it all in one shot here. Negative 8 times the first coordinate of u plus 9 times the first coordinate of v. Give me my first coordinate of the answer. And then we've got negative 8 times the second coordinate of u plus 9 times the second coordinate of v, and so on. And I just calculate all of that, and we're going to get 24 and 45 makes 69. Negative 16 plus 0 is negative 16, and negative 32 minus 9 is negative 41. Okay, we get that vector there. A vector in R3, it's got 3 components. Now lastly, here I've got an example where I'm taking my scalar to be 0. So I'm going to multiply every component by 0. You probably already figured out exactly what's going to happen. Here I'm multiplying the components of u by 0. And it is not a surprise at all that we get a vector 0, 0, 0. Of course, if I multiply every component by 0, all the components are 0. This we call a 0 vector. Okay? And sometimes we use the notation 0 with a little vector symbol on top of it. So there's some basic vector arithmetic. We've seen now vector addition, vector subtraction, and scalar multiplication. We are very careful to use that whole phrase, scalar multiplication, for the last one, because it turns out there's different types of multiplication. Now that's really weird when we talk about vectors. So when I talk about this type, I have to say scalar multiplication. We'll see another example of another different type of multiplication type thing next week. All right, so let's just talk about some abstract properties of this vector arithmetic here. We have a big long list that has to be true for all the different vectors. We mentioned already the 0 vector, okay, and we use this 0 with the arrow above it to denote it. Now, if you take a look at these 8 rules for vector arithmetic, they're pretty obvious. At least they're pretty obvious for vectors in Euclidean n-space. But the truth, the scary truth, is that you can have vectors that aren't in Euclidean n-space, where the vectors themselves are functions, or are things called matrices, or any sort of weird mathematical object. So really what all of these rules are is they're the definition of what's called a vector space. Now I do not want you to memorize these at all. Yeah, just showing them to you for now so that when you see them in your later courses, you might kind of remember. So let's just very quickly go through them to see what they're saying. The first one's saying that for u plus v, that's the same as v plus u. If you change the order in vector addition, it doesn't matter. That's pretty obvious. Number 2 says that if you have 3 vectors, which order in which you add them up, it doesn't really matter if you're adding up all your vectors. The third rule says that if you take any vector and add the 0 vector to it, clearly you will get the same vector you started with. The fourth one is saying, well, and that third one is really saying there is a 0 vector. And what is its property? You add it to any other vector, you get the vector you started with. For us, it's the vector with all zeros, but in weird vector spaces, the 0 vector might have nothing to do with the number 0 at all. It can be very weird. For number 4, what we are talking about there is that for every vector, there's another vector, let's call it negative v, so that v plus negative v is equal to the 0 vector. So that means that every vector has what we call in the business an additive inverse. Okay. Now again, this is completely obvious. All we do is switch the signs on all our components. That's completely obvious. But in other very strange vector spaces, exactly what the relationship is between v and negative v is not clear. The fifth one says that if we take a scalar multiple of a scalar multiple, we might as well just have multiplied the scalars together to start with and then done one scalar multiple. Rule number 6 is basically a distribution law. It says you can distribute a scalar to both terms if you've got a sum in brackets. And then 7 is kind of the flip side of that. If you're adding two scalars together, you can kind of distribute that as well. And the last one is kind of saying that there is a scalar, let's call it 1, where if you multiply that scalar by any vector in your space, you get back your original vector. And again, for us, it is the number 1, but for other weird vector spaces, it might not be a number at all. It might be some kind of weird object. So again, the whole purpose of showing these to you is to let you know that vector spaces are much bigger and stranger and exciting than the little glimpse we're going to get in this course. And you'll see more of that in your linear algebra course. But just to practice all of this, let's go ahead and try a few examples. Basically see how we can simplify vector expressions. So if I take 5 minus 3 and I multiply that by u plus v, well, I'm allowed to simplify that scalar first. And then if I take just a quick look up at law number 6, well, I can just distribute that too. Okay. For the next one, what we can do is we've got that negative 1 scalar in front of the second pair of brackets. Again, by law number 6, we can just distribute it in. And those first set of brackets really aren't serving any purpose. So we can just write this as 3u plus w plus negative 1w plus 7v. And this is by law number or property 6. Again, you do not have to refer to these ever when you're doing your work, just so you can see kind of what's going on and how it's connected to that list of properties. And then we can add these up in whatever order we want. So those w's in the middle, I might want to add them together. And it looks like w plus negative w, well, that should give me the 0 vector. Let's be pretty fancy about this and formal. So that was by law number 4. And lastly, if we add the 0 vector to anything, by law number 3, we get back what we started with. So this is just 3u plus 7v. That's by law number 3. Okay, and we can try some other examples here. Let's give ourselves more defined space here. Again, I can distribute this negative 9. Okay, and then I can reorder this however I want. That's based on rule number 1. So this first one was by 6. So I could say put the parts involving v side by side. So that's by law number 1. And then we get 37v minus 18w. And as for the last one, if I just take a look at the last little bit there, I can see that this is 6 times some number. This is all a scalar. But I have over here v. 1 times v is v minus v. So that's by law number 8. And then v minus v, well, by law number 4, that's the 0 vector. And then if I multiply the 0 vector, it really doesn't matter what the scalar is, all my components will be 0. So I don't really need to go much further than that. If you want to calculate the scalar, you can, but we're going to end up in the same place regardless. So there's a little bit of simplifying involving vectors. Notice for this problem, we had no idea what the actual components of u, v, and w are. We were just told they're in the same space. We don't even know what that space is. Maybe it was R7, maybe it was R19. We don't know, and we don't need to know to make these simplifications. Alright, so we'll continue along. And now we'll connect this back to a nice picture of vectors. So if I have some vectors in the Cartesian plane in R2, Well, let's draw two vectors in R2. So there's a vector. We draw them with these as little arrows. I don't know, I'll draw another, maybe a third vector here. Okay, so we have three vectors there. Now, we call the pointy part, we call that the head, and the back end we call the tail. And all that matters, and you may have discussed this in your physics class if you've taken a physics course before, all that matters for a vector is its magnitude, how long it is, and its direction, what direction it's pointing in. And in fact, two vectors are equal provided they have the same direction and the same magnitude. So if I look at the green and the blue, they have different lengths and they have different directions. Those vectors are completely different. But if I look at the red and the blue, they look like they point pretty much in the same direction, and they look like they're around the same length. So even though they're drawn in different places in space, they are the same vector. Now this is a bit stunning, because usually when things are the same geometrically, in the Cartesian plane, it means that they're occupying the same space. But that's not true for vectors at all. Okay? Vectors aren't fixed to any point in space. They just have a magnitude and a direction, a length and a direction that they point in. So if I ever find two vectors that have the same length and point in the same direction, they're not different vectors, they are the same vector. Now this can get a bit confusing. I can have a lot of different vectors all over my space, and I'd like to know, well, maybe some of them are the same. How can I tell? So one thing we do is we put our vectors in standard form. So what we do is we move them so that their tail is at the origin. And if I put them with their tail at the origin, kind of fix them to that point in space, and there I see that they lie perfectly on top of each other, well, it means they've got the same length and the same direction. And that's the only way they can have the same direction, if I've put their tails at the origin. So it's a good way to compare vectors. So we're going to draw some vectors in the Cartesian plane. Now if I put a vector in standard form, the connection to the algebraic components are that in standard form the tail is at the origin and the head is at the point given by the components. So these are coordinates of a point, they're also components of the vector. So let's see how that works. Draw the Cartesian plane here, and we'll draw these two vectors in standard form. Their tails will be at the origin. So if I draw u here, its head is going to be at the point -1, 2. So the head is going to be up here. The tail, since it's in standard form, will be at the origin. That's the vector u right there. Now, if I find the point 3, 4, or sorry, 3, -4, so then the head of my second vector, v, is over there. So I've drawn my two different vectors in standard form. And so standard form allows us to have a bridge between the algebraic components and the geometric picture of the vector in the Cartesian plane. That is, by using this method, by putting tails at the origin, you can take the components of a vector and draw it, or you can take the drawing of a vector and figure out its components. All right? So let's understand now, what if my vector isn't in standard position, like some of these vectors up here? How do I move them to put their tails at the origin so that I can figure out the components of those vectors? Well, let's just imagine that we've got a vector, or vectors u and v, with the tails and heads given here. All right, so my vector u has its tail at 1, 4, right there, and its head is at -2, 3, so over here. So my vector u is right there. It's one way of drawing it. Now my vector v has its tail at -3, 4, so right there, and it has its head at 2, -1, right there. Okay. Now, I'd like to put those vectors in standard position so that I can write their algebraic components. Well, how do we do that? I know to put a vector in standard position, I need to move its tail to the origin. So let's think about the vector u. If I move its tail to the origin, I go down 4 units, and then I go left 1 unit. Okay. Well, if I do that to the tail, and I want to slide around this vector without changing its direction or magnitude, I can think of it written on a clear piece of plastic. So if I slide the whole piece of plastic down 4 units and left 1 unit, that'll move my tail to the origin, but it'll also move the head exactly the same directions, down 4 units and left 1. So I'd go down 4 units here, and I'd go left 1. So that means that my vector u, the head is going to be at -3, -1, and the tail is at the origin. Okay, and if I look at those vectors, they look like they are pointing in the same direction and the same length. But now u is in standard position, and I see that the components of u have to be -3, -1. Now if I take the green vector, what do I need to do to it? I need to move the tail again down 4 units, but this time right 3 units. So I'll do the same to the head there. So I'll move the head down 4 units and to the right 3. And we get that v is the vector 5, -5. Okay, so I can very easily find the algebraic components of my vector by doing this. Now there's a little bit of a shortcut. Can you see it? If I look at the coordinates of the head and tail of u, can you see a little arithmetic you can do to find the components of it immediately without having to do any drawings whatsoever? Well, if we take the coordinates of the head and subtract the coordinates of the tail, we're going to get it. So u is going to equal, -2 minus 1. That was exciting. -2 minus 1. And the second component will be 3 minus 4. So we get -3, -1. For v, we'd have 2 minus -3, comma, -1 minus 4. So that would give us 5, comma, -5. So then we don't even need the picture at all if we just want to find the algebraic description of our vector. Okay. Now, just to reiterate these key ideas here, notice that two vectors in 2D are going to be the same if they have the same length and the same direction, and that's true for any vectors at all. So the position of the head or tail is kind of irrelevant provided their length and direction is the same. And notice that two vectors can only be the same if one is a translation of the other. That is, if we drew one on a piece of plastic, clear plastic, and we shifted it around, up, down, left, right, we could put it right on top of the other. So we'll talk a little bit more about the connection between the arithmetic, the algebraic arithmetic of vectors, and the effect that has on their picture later in this week's classes. Thank you very much.